So welcome to today's seminar. I'd first like to take a moment to acknowledge the traditional owners and their custodianship on the lands in which we meet today, which are, for me, it's the Turrbal and Yagara people. And I pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. And we recognize their valuable contributions to Australian and global society. I'm Rennie Lee. I'm one of the LCC seminar coordinators. And so welcome to today's seminar. I just want to note that this is also Social Sciences Week, which is an annual event that celebrates and showcases the diverse range of social science disciplines and research in Australia. And the social sciences are key to understanding humanity, society, and the institutions which govern our daily lives. So today we have two presenters, Rajith Vidanaarachchi and Jason Thompson, both from the University of Melbourne. So Rajith is a Life Course Center Research Fellow and a researcher at the Transport, Health, and Urban Design Research Lab at the Melbourne School of Design. He works with agent-based models and researches how to make them better. He's also an educator at the Department of Mechanical Engineering, where he's the head tutor for AI for engineering and numerical methods in engineering subjects. So his main research interests include fair and ethical AI, optimization, and pattern recognition, and community analysis. So both Rajith and Jason are coming to us from Glasgow, it's nearly 2 a.m. for them. So just want to say, give them a warm welcome and thank them so much for kind of giving this talk at such a very early or late hour, depending on whether you're a morning or night person. So with that, I think I'll just let them get started. And yeah, go ahead. Thank you so much.
Thank you for welcoming us. And I would also like to acknowledge the traditional owners and their custodianship of the lands on which we usually live in and work on, and pay my respects to the elders, past, present, and emerging. And yeah, today we are joining from Glasgow, me and Jason both, because we are here for the Social Simulation Conference, very pertinent to today's talk. So let's get started. Thank you everyone for joining in. So we'll be learning about agent-based models for understanding social systems today. And before we go in, let me ask you a question. Are you a modeler? So maybe if you can use the reaction buttons to tell me whether you think you are a modeler, that would be great. We are getting a few reactions, and thank you for that. So I think for every one of us, the answer is yes, because everyone is a modeler. Because if you are doing any kind of thought process on thinking about any kind of a problem, by default, it is a model. It could be just an informal model, but the difference is that the formal modeler explicitly writes down what their model is, while the informal modeler keeps the model in their inside their head. So just without communicating the model, they are still using a model. That's why the decision to not use a model is also a model when we are analyzing any kind of a problem. So this is concept from complexity science and systems thinking approaches, that we use some kind of a model when we think of any kind of a problem. So when we are thinking about complex social environments, there's a few types of models that we usually use. We use state charts, causal loop diagrams, system dynamic models, and then agent-based models. So we'll be building up to agent-based models in today's talk. So why do we model? Why don't we just go in and give a solution to the problems that arise around us? So this is probably the first question we should answer before going into learning about agent-based models. Why do we model? So the most common answer to this seems to be to predict what's going to happen. But I would like to mention that it's not just about prediction. There could be a plethora of reasons why we choose to model something. So, for example, it could be to know like what kind of data we should be collecting, or it could be to educate the stakeholders on what's going on, or to offer crisis responses in real time. So there's so many different scenarios where we may need to use modeling. It's not just about prediction. So going ahead, why do we need models? Because we are all human here. Hopefully all of us here at today's presentation are human. So we are not that smart to be thinking about everything at once, especially when we are looking at complex social problems. We can't be keeping track of like so many different variables and parameters. So beyond a certain level of complexity, our ability to remain rational is quite limited, and we'll be incorporating a lot of biases into the process. So this is why we need to model. And also, we usually have limited time to make decisions and limited capacity to evaluate and process information related to a crisis scenario. So this is why we should be using models, because otherwise we would be limiting ourselves. And also because systems are quite complex, and there's multiple inputs that we need to be thinking about, and nonlinear interactions. Problems are evolving over time, and there's interactions going on, and there's a local context in each of these interactions. There may be feedback loops coming back into changing something in our system. There could be different evidence there, the competing truths, and we are all biased in terms of the data that we have collected. So especially when looking at this complex nature of systems that we really want to model. And I know this is not a Picasso, but it highlights the fact that we need lies that help us see the truth. So a good model is not the real world, because we don't need an alternate real world, but we need an analogy of the real world to be able to think of it better. So we want to have models so that we can answer questions of what's going on here. And a good model will let us reveal the most important dynamics of a problem and strip out that noise away, so that we can focus on what really matters. So that's what we are looking out of a good model, an abstraction of the real world scenario that helps us build a narrative and to understand what goes on here. So models should be quite explicit. They should tell us directly what is going on here. We don't want models where there's some sort of thing that happens and then suddenly there's a black box or a miracle and then we have results, especially if you are working with policy oriented modeling, especially where the things we are modeling will affect the general public, and especially because we live in a democracy, whenever we are engaged in modeling which would affect the policy, it should be quite transparent and explicit. So we can't be just put numbers into a model or put numbers into a computer and get some results and say, okay, this is our model. The computer was our model. So a good model will be simple to understand. I think it should be simple to explain to stakeholders. And while we can have some randomness and probabilities, we should be able to use that to reflect uncertainty. Still, it should be explicitly stated, this is how we do uncertainty in this model. So these are some good qualities of models. But also, there could be a crisis. So who needs crisis? Because especially when we are modeling, we do want crises, because we would rather that this crisis happen in our model rather than in real life. So especially we want small failures within the model so that we can correct the course in the real world scenario. And we don't want big catastrophic failures in our systems or our institutions. So this is why we need modeling to understand, oh yeah, this kind of failure, that's all right, it happens every day. But this other particular type of failure, we want to avoid that. Signs of that kind of failure, we want to know, okay, this is what we want to avoid. And this is what's shown on the right hand side. It's some graphs from COVID modeling that we did in our research group. And this shows what we want to avoid as a catastrophic system failure. So if you can see the lines here, we are looking for, so these are COVID cases. So we are looking for nice gradual reduction of COVID cases, and where the cases remain at zero. We don't want a scenario where the COVID cases bump up. So this is a scenario where we have several policy scenarios, and we apply these different policy parameters to our artificial model, and then these different interventions may reflect, oh yeah, this kind of policy parameters, these are good, but this other kind of policy parameters, they don't seem to work. It will drive the cases down for a little bit, but it will definitely bump up again. So because we can create these crises and failures within an artificial society, we can test them out with policy solutions within the artificial society as well. So this is another great utility of agent-based models, being able to create little models of artificial societies so that we can do testing in this simulated world rather than in the real world. So let's revisit those different kinds of models that I explained earlier. And the state chart. So we have a very simple form of models here. So most of you would be quite familiar with this kind of modeling. Very straightforward, and usually usually the processes in our institutions that we follow day to day have some sort of a flow like this. We may not be following it exactly. In fact, no one exactly follows this state charts, but this kind of modeling gives an understanding and it formalizes a process. While we may not follow this kind of a model in reality, when something goes wrong, we are able to say, okay, it's going wrong around this particular area. So this is where we need to check. So this formalization of a process, or like having a formalized understanding of the process, it helps us to intervene when necessary. While when things are going well, we may not need it, but when things start going bad, that's when it's really beneficial to have this kind of a formalized understanding. And then we have causal loop diagrams, taking it a little bit more dynamic than before. So this is where we have systems where everything is interconnected and something affects the other, and then it comes back and affects something else. For example, we have a model that we have built for WorkSafe. And for example, if we take some of these, it may be quite small on your screen, but I'll just go through one of the loops. So here we have unsafe jobs that results in more injured workers, and then that results in negative physical health. So this kind of a very simple causal loop diagram would help understand dynamic processes and also feedback loops that may exist within a system. And then we have system dynamics models, which look into systems, but in greater detail. So this can't be read I'm well aware. So we have a zoomed in part of it. So this is very similar to the causal loop diagrams, but then we have more parameters in there so that we can understand the system in a little bit more detail. This was also used for WorkSafe. And here, for example, you can see a close-up of a scenario case where we can build multiple scenarios and see what are the effects of these scenarios. So this is the kind of modeling that we like to do. And now let's get into So usually modeling exercises will result in interactive dashboards so that we can play around with policies, so that we are able to have a thorough understanding of the system that we are modeling. So now let's come back to ABMs, the topic of this talk. What are ABMs? They are something from computer science, but then we have this trifecta of computer science, and then the discipline of science, and then you have applied mathematics. And in this field, we have in this intersection, we have computational sciences, and ABMs is a computational model that we use to represent real social system. And in ABMs, we can have a blend of existing empirical knowledge, and then we have computer science aspects, but also we have mathematical models. So this is a really powerful tool that we can utilize to simulate our real world social scenarios. And ABMs consist of agents. These are individual intelligent entities that think of their own and act of their own, and they interact in a simulated environment based on explicit local rules. So each agent works by themselves, but the rules are explicit. So we know what's going on. They are very explainable. And how do we derive these rules? These are from existing research evidence or expert opinion. This could be through stakeholder consultations. This could be through literature reviews, where we identify these rules. these rules could come from quantitative data, or this could be from qualitative data, depending on the system. As long as we have a system to formalize what's happening within these interactions of an agent, we can make that social system into an agent-based model. And why use ABMs? Because ABMs are safe. We can experiment with the system, and we can introduce risky policies to see what happens. No one actually gets hurt except for our computational agents. So it's a really good place to do experimentation with policy. And they're quite cheap, because running an actual experiment in the real world, scenario 1, scenario 2 kind of testing, that's quite difficult and expensive, and also unethical, because these affect real people. While when we do this within a computational environment, it's much cheap and also quite flexible. We go through some kind of a scenario and we think, oh, actually that kind of testing may not be as informative as we thought that it would be. You can change it. It's so much more flexible when no real humans are harmed or involved in the process. So this is why agent-based models are quite a nice tool when we are exploring social systems. So how do these actually work? So we model behavior of thousands of individuals that exist within this social system. So this could be a welfare system, or the housing market, or in case of the COVID modeling, just an everyday urban city. So the difference is that we calibrate these thousands of agents to the real world. This could be through demographics, through geographical information. And by doing this calibration, we create an artificial society of individuals who are generally trying to achieve their own goals in their own ways. These agents are quite heterogeneous, because they could have different thinking processes, these different priorities, which we have calibrated according to the real world experience. And these goals could be, for example, in a welfare system, getting services, or in a hospital system, these individuals would want to be getting better. In the housing market, these individuals may want to be moving on to a better housing situation. So we have a little artificial society where these individuals are interacting with the environment, with each other. And the important thing is we have stories of individuals. So for example, let's say there's one individual who's injured and wants to make a claim in an insurance system. And we have stories of these individuals going through the system, which we call micro actions or micro deliberations. And this is actually what we know from a society as well. We know stories of individuals, and then within an ABM, we put all these individual stories into the simulated environment, and we bring all these stories together, and then we see what happens to each individual. Where do their stories end? And by doing so, we can see what happens within the entire society. It's not just an average story, because we get a range of individual stories and behaviors, and this is where we get a macro pattern emerging. So we have this micro behavior and a very individual decision-making processes, very individual cognitive processes that goes into the system. And as a result, we see macro changes or macro dynamics, macro patterns emerging within the society. So this is an overview of how agent-based models work in making us have a better understanding of a social system. Going a little bit into a technical side of it, an agent-based model will have some kind of a model backbone under which we can visualize how individual agent interactions are happening or how agents are navigating a system. And then we have our agents here. They will be interacting with other agents or different groups, and there could be different groups of agents who are navigating the system. So, and then we may have like different submodels within the system. So it could be as complicated as we want, hopefully not too complicated, or like as simple, like a good abstraction of the real world as we discussed earlier. And then we have these individuals who are talking with each other. So let's see like who these individuals are within an agent-based model. So within an agent-based model, our agents will have heaps of data incorporated within them. We'll have demographic data, we'll have data around attitudes, needs, norms, values. So these are quite important to determining how individuals interact with each other. So while we have all this demographic data or financial, economic data, we also have these inherent cognitive attitudes and needs and norms integrated into the system as well. And then we have social network data for individuals to see who they will be interacting with. And any kind of data source you have and want to incorporate into an agent, this is possible within an agent-based model. And okay, now we have a description of an agent and what is represented within an agent. Now we'll go and have a look at what happens within the agent's brain. So this is basically the brain in an agent. We have the agent and we have the environment around the agent. When we say the environment around the agent, this will incorporate the other agents in the system as well. And our agents will have sensors that tells them what the world is like right now. And in a very simple agent-based model, these agents will have condition action rules, which tells the agent, okay, this is how the environment around you is right now. So this is the action that I should do now. And then agent has effectors or actuators that takes an action. So this action of an individual affects the environment. So we have this loop going through where agents interact with the environment. And this is just one agent. And we have thousands of agents interacting within this environment. And this is what makes this micro deliberations or micro actions roll onto a macro pattern. And just to say, these agents don't need to be as simple as that. There are multiple ways in which we can make this agent's cognition complex and interesting. So we can have different kinds of agents depending on the problem scenario. So the cognition could be quite rich within an agent-based model. And what we get out of an agent-based model is not just snapshots in time, but what we can see is how the system changed through time, because we put these agents together and then we run it for uh, as many time steps as necessary for each scenario. So here we have the system where patients access different systems, and then we are monitoring the number of active patients in the system. And then we have these different policy decisions that we have made, and for each policy decision, how the system reacted. So this kind of modeling gives us a nuanced understanding of how different policies affect the systems, but also it gives information without affecting real users. So while this is an abstraction, it will give us a really good idea about what we can expect in the real world. And we will have some other examples from other areas. So these could be used for various examples as mentioned here. But from our research group, the gem of the models we've made is modeling Victoria's escape from COVID-19. And Jason, who led that project, is with us today to take us through the COVID model and to explain how agent-based models were super useful in tackling Victoria's escape from COVID-19.
Thanks, Rajith. I might just have to get you to step through the slides, if that's okay. Hi, everyone. Nice to see everyone here. I suppose what I want to emphasize here is not so much, I mean, we can talk about the COVID model, but I really want to talk about the intersection between agent-based models and policy models. So the main thing that we try to do with agent-based models, and the thing that agent-based models should allow us to do, especially in the social sciences, is to model policies and policy interventions. So the reason why the COVID modeling that we did in our group and how it differed, I suppose, from more traditional epidemiological models, it was specifically built as a policy intervention model, not so much an epidemiological model. It had functions within it, which obviously were about the epidemiology of the crisis. But what it really did was enable government to experiment with different policies around school closures, business reopenings, the numbers of people who were essential workers at any time, people's movement restrictions, etc., etc. And it was a model of how to release all of those restrictions without us going into an oscillation where we're just in and out of restrictions all of the time. And remembering that this was built pre-vaccination, so we only had our non-pharmaceutical interventions to look at. So we tried to build a really generic, but in Victoria's case, a specific policy model, and this is the power as Rajith has mentioned too, of agent-based models in the policy space. So we had used the model. We'd been developing the model with other colleagues across the university, School of Population Health, and other universities, School New England, etc. And we'd been looking at the way in which policies were affecting COVID cases. And early on, we sort of said, look, we think that New Zealand is going to get to elimination, but we think Australia is going to rebound into a second wave. And so we suggested that was going to happen based on our policy settings and our thousands of model runs that we did. And unfortunately, that happened, of course, in Melbourne, down in Victoria. So we were the unlucky recipients of that second wave. So we had a bit of a track record with the model that we had built, but when we're in those really dark days of the stage 4 lockdown, and we were isolated from the rest of Australia, and we said, look, while we're here, we still think that there's a possibility of elimination, and that was important at the time because there weren't any other states that had active outbreaks, and Victoria was never going to be able to rejoin the rest of Australia if it had large active outbreaks. So it was a really difficult time, of course, for Victoria. But we did think that there was a possibility for elimination. And given that we're already in really hard stage 4 lockdown, we thought, okay, well, what's the possibility of elimination? We collaborated really closely with public servants. I know many people on the call today will have contacts within the public service, and so this collaboration with not only our areas of expertise, but the way in which they were thinking about policies and what was possible in the policy space was really important as well. So agent-based models are really great for participatory model building. You can take you might be a domain expert, but you might have other people, other stakeholders who they know how the system works, and their knowledge can be incorporated into those agent-based models to make them as realistic as possible. So in this case, reliance on people from inside the Department of Health was really important. We talk a lot in our group about how to use these models as well, and we talk about 3 principles. The model has to have instrumental utility, so it has to be useful. It has to have conceptual utility, so it needs to be explainable, and it does ultimately need to have political utility. It's no point, we've all had the experiences of presenting evidence to policymakers or evidence to the people that we think should be making a decision around the evidence that we think is important, and not having that evidence listened to. But it was the evidence that matched what the government at the time also wanted to know as well. So we had those 3 elements, and that's why that model was used. So we'll just skip through these in quite quickly. But these are the slides that Victorian government used to explain the model that we had created for them. So it did have these elements of prediction. So we're trying to sort of say, okay, well, this is the pathway that we think that the Victorian government will take here. So it was trying to also understand these uncertainties as well. We were trying to explain what we were trying to avoid. So we're trying to avoid this oscillation pattern where we came out of restrictions, we had a couple of weeks of sunshine, and then we just went back into them again. And we were trying to think long term as well, so not just the next week. And we're also trying to explain the uncertainties. The model, unfortunately, history only happens once. But in our models, we can make history happen thousands and thousands of times. So we're sort of saying, okay, well, if we want the best chance of being able to escape from this second wave, these are the sorts of conditions that we need to be able to produce in our society to stop that oscillation pattern. And in communicating risks as well. So this goes back to the points Rajith made about explicit and transparent models. We were sort of saying, okay, well, these are the risks that we think are associated with different policy settings. So the risks of going back into lockdown before Christmas again under different policy settings were spelled out for both government, and they tried to use that to spell it out for the community as well. And if you're interested in, I suppose, we ended up publishing this work in the Australian New Zealand Journal of Public Health. If you are interested in reading about both the process and the model itself and how that was used, then I encourage you to have a look at that paper.
Yeah, so we can create frameworks for social systems of interest. Like a lot of us coming from different areas of social science will have different social systems of interest that they'll be really interested to try out agent-based modeling on. So we can use agent-based modeling to test policy scenarios, communicate the results from policy modeling, and also to understand heterogeneous populations, basically to have a thorough understanding of a social system, and also to communicate these results to policymakers. We can really create systems of interest with agent-based models. And if you're thinking of these things, what are factors that's driving social systems or outcomes or metrics? And if you want to restructure the social systems, or you want to know how or when to implement policies, and overall, if you want to avoid system collapse, and if you want to make a good change in this world, ABMs are for you. And think we are right on time. And thank you everyone for listening to us pitch about agent-based models to all of you today. And we'll be here to take questions.
I had one myself, if I could start. And I was wondering about what are the data requirements for agent-based modeling? Does it, from my understanding, do you need like large, basically administrative data sets, or is that kind of what's like the ideal data, and what could you work with even if you didn't have the ideal data in order to do these kinds of models?
So that's a great question, and it reminds me of an ongoing project that we are doing with the Tati Tati nation around their water and land sovereignty. We are building a model around the issues that stem from lack of water rights for the Tati Tati community in the Murray-Darling River Basin in North Victoria. And especially when it comes to these communities, data is quite scarce. We don't have a proper census data, or census data is underrepresentative of the indigenous communities. And we are building this model purely through qualitative data, and the data that we acquired through storytelling or yarning. So agent-based models are quite powerful in the sense that we can capture data that could be sparse, or that when there's no quantitative data, we can still capture the society that we are talking about through qualitative data. But when you have rich data, then it's of course quite useful. But if you are missing some data, then, and if you have some other proxies that we can use, we can still build a good agent-based model. Jace, do you have anything to add to that?
Yeah, just to add to that, it depends. It depends on how closely calibrated you want your model to reality, and that often depends on how much you really want to predict. You might want to make a point estimate kind of prediction rather than what we were sort of talking about before as, okay, well, let's build a model that explains a process and explains dynamics and explains the way, let's say, a housing market might go up and down, or the way in which social welfare or insurance projects or programs might benefit some groups over others, or something like that. So if your model is more explanatory, you probably don't need as much detailed data. But if you're really looking for prediction and you really want a calibrated model because you're trying to predict, which is actually very, very difficult in social systems anyway, then you want to have as much data as possible. But the great thing about agent-based models is they allow you to start with, they essentially allow you to start with zero data. They allow you to start with theory, and they allow you to start, and then you might sort of fill in the data blanks as you need to go. But there's no reason for you to have to start with data. There are plenty of people who build theoretical models. It might be social systems, or it might be opinion dynamics models or something like that, and they're purely built on theory rather than data. So the data is actually comes out of your model as much as goes into it.
I guess while we're waiting I might just ask you another question, which is, are there, in terms of like the program that you use in order to build these models, you could talk a little bit about that as well?
Yeah, so there's various programming tools that could be used to build agent-based models. Most non-programming or non-computer science folks tend to use NetLogo, which is very simple interface-based agent-based modeling platform. but you can still incorporate rich decision-making systems within an agent-based model using NetLogo. But then if you're comfortable with one of the major programming languages, every programming language has its own agent-based modeling library. So be it C, C++, Java, Python, Julia, there's various platforms for that. And then if you want to have something, let's say GIS related, strongly married with geographical data, then you have agent-based modeling platforms such as Gamma, that's particularly designed to be used with the geographical systems. So yeah, there's a plethora of options out there.
Great.
Depending on the use case, depending on the people involved in the modeling, you can have your pick.
That was really interesting. I can see lots of applications, and it seems very relevant to a lot of the work that we do in the Life Course Centre. And I'm not sure if this is a question, I'm not sure how easy it is to answer, but one of the things we said in the latest bid for the Life Course Centre is that we wanted to move away from thinking about averages, because we felt that, everybody, things are different depending on the community that you're in or the particular context. And we wanted to kind of get away from kind of talking about on average, relationships or correlations. And I'm just wondering, from something that you said in one of the earlier slides, suggested that, these kinds of models might allow us to do that, because the results are not taking all of the behavior and kind of converting it into an average, but looking at how individuals kind of putting all the individuals together and then getting some kind of solution. So is that an appropriate understanding, or have I misunderstanding what you said?
That's an excellent understanding, Janine, and I think both Jason and I are quite passionate about exactly this, stemming out of agent-based models. Because let's say we have a system and we have let's say 40% of our agents experiencing and one extreme outcome, and then we have 60% going into the other extreme. And if we average this out, we are not getting any of their stories right. So I'm quite a proponent of using a probability-based understanding of outcomes, so that we capture everyone's story and not just water it out with averages. But I think Jason would also probably like to say something about this.
Yeah, absolutely. Well, the point you raised, Janine, is exactly why I got into agent-based modeling. And it might seem strange, but sometimes the synthetic societies or the artificial societies that we create are more realistic than the real societies or the real samples that we see studied, especially in social welfare systems or something like that. So my background is in social welfare systems, disability systems, social insurance systems, and often we would have people come to us with evidence about samples that they'd had from an injured population or something like that. And of course, for internal validity, you clean up your sample. You get rid of people with dual diagnosis. You get rid of people with a head injury. You get rid of people with some other complicating factor, which means that they can't fill out the survey, whatever it might be. And of course, when you're actually managing a social welfare system, these are the people who the extremes are the people who drive both the policies and the often the outcomes of that system. And to remove them is for internal validity purposes. And so your distributions are even, or whatever it is, or normal, it just doesn't translate into reality. So the heterogeneity aspect is again one of the great strengths of using agent-based modeling, because in so many of the systems that we're talking about the average, it really doesn't make much sense, especially in terms of service use or something like that. There are often power laws where it doesn't actually make any statistical sense to talk about averages as much as it makes sense for individuals. So quite passionate about that area, and in fact, it's what drove me into this field.
Thanks, Reddy, and thanks, Jason, Rajith. I mean, I know I've spoken to Rajith about use of agent-based models, sort of in the context of a housing market, and I suppose I'm still trying to understand exactly what the agent-based model is, because I think about something which looks at the housing markets and those models which do that. There's micro simulation models, which, you could sort of think they take a large data set and the individuals in that large data set and sort of think of those, their behavior and aggregating that behavior up, in response to changes in prices and things like that, and trying to understand what the outcomes are. And then you have more macro models, where I think this is close to the agent-based modeling, where you might have a series of representative agents. So, for example, you might have individuals less than 30, individuals between 30 and 40, and over 40. So, a series of, so to speak, representative agents, rather than, thousands of observations of individuals and their behavior. You have sort of, I suppose it's similar to synthetic type cohorts that you're thinking of. And within that, you can sort of model the behavior, and in particular, model the behavior subject to constraints. I mean, I think that's the key thing in the social systems. I'm an economist, and so thinking about it from an economics perspective, we usually think about individuals making choices subject to prices they face and the incomes they have to, choose the housing outcomes which they prefer. And I suppose if you've got any thoughts or insights into that's the use of agent-based modeling, that sort of framework, when those constraints are very important, I'd be interested to hear. And in particular, I suppose I'd be interested to know if there's anywhere we can look and sort of see an application of an agent-based model and try to understand, I say, the scope of it, like whether it's 100 equations or 10 equations which define the agent-based model, and in some sense how it's solved.
So the agent-based models, agent-based models try to deal with systems that are intractable, often from a solution perspective, if you like. So if the degree of heterogeneity that you generally get, feedback mechanisms, loops, emergent phenomena, etc., mean that they're working in an unsolvable space, a transparent space at an individual level, and you can trace what's going on, but not really the sort of not the sort of models that would generally reach an equilibrium or something like that, because there's so much dynamics going on in them. So they're generally used in, I'm trying to think about, there's a whole area of agent-based modeling in economics. So there are housing market agent-based model people who specialize in that across the world. There's people who look at agent-based modeling in an economic context in, let's say, industrial changes or changes in technology, et cetera. We have there's I'm happy to I could send to you some of the people who work in that space, and that might be, I'll give you some papers in that space, and there's certainly some people here at this conference who do that kind of work as well. So I'm more than happy to send those sorts of things to you as well. I know some people at the Melbourne Institute as well have been interested in agent-based modelling, let's say in labour market dynamics or healthcare distribution, et cetera. So I think there are some people over in economics who have had a bit of a focus in ABM, at least in the Melbourne node.
Thanks, Jason. So I'm conscious of the time. There are two questions in the chat, and I'll forward them on to you, Rajith and Jason. One is from Haley about just mentioning that the COVID modeling work was amazing, and she was interested in kind of asking about other policy level spatial type examples you've used. And then there's a question from Richard Morse about how you validate these models and how do you know they work. So I'll just forward those on to you. But I just want to say thank you again to Rajith and Jason for our wonderful talk. if anyone just in the audience, if they'd like to in the future do a seminar, please let us know. And a recording of this seminar will be made available in the next few weeks. But a warm welcome again, or a warm thank you again to Jason and Rajith for giving this talk at such a late hour for them. So thanks so much.
Thank you, everyone.